Hey there, Mr. Weaver here, and this is Lesson 5 of Topic 4b, Solutions of Two-Variable Inequalities in Context. After this lesson, you need to be able to write an inequality from a word problem, and you need to be able to graph the inequality and solution set, and explain what it represents in the context. You'll know you're successful if you can write an inequality from context, you can graph and shade the solution set, and you can explain what the solution set represents. First, before we get into some of these word problems, we need to know some words to look for that help us determine which inequality symbol to use. First, let's look at some words that mean less than. So here we're talking about the expression is usually less than a total. Some words that you're going to see other than just less than might be under or below, fewer than, smaller than, and there might be others. These words mean that it's less than a total, but it can't be equal to that total. Less than or equal to, where it means that it is usually less but could also be that number. Here are some words that fit that situation. So we could see at most, maximum, or no more than. Notice these are kind of all like backwards thinking. They're all dealing with the most. So the most that it could possibly be is a certain number, but usually it's less than that. If we see greater than, where the expression is more than the total, then we might see over or above, more than, larger than, bigger than, and again, that's just some, not necessarily all of them. Finally, instead of greater than or equal to, we might also see at least, and that's a very, very common one. Or we might see minimum, the minimum amount, or no less than. Again, those are kind of the opposite thinking of what the symbol is, because that's the lowest it could possibly go. Usually it's higher. When in doubt, think of an easy situation where something might apply and picture yourself in that situation. Would you need to have more or less? And could it be equal to the number that is the boundary? So let's look at a couple examples of writing some equations and graphing what the solution set looks like. Fernando wants to buy X pounds of strawberries and Y pounds of blueberries from the store. He can only spend $15, and blueberries cost $3.50 per pound, and strawberries cost $2 per pound. What inequality represents the possible combinations of fruit? So here's a common situation. Someone goes to the store. In these kinds of situations, we're usually buying an item. In this case, we're buying fruit, and we have a certain amount of money that we're allowed to spend. We could spend all of the money, or we could spend less. We only have a certain amount of money. There's no way possible to spend more. So here, buying fruit could be less than or equal to $15. So when we're buying fruit, we have S and B. Together, that's our combinations of fruit, and we need it to be less than or equal to 15. If we plug in the prices, Q is the price of strawberries, and $3.50 is the price of blueberries. Still, they have to be less than or equal to 15. This in itself could be a good inequality to use. However, it does tell us that we want to buy X pounds of strawberries and Y pounds of blueberries. So I'm going to switch X and Y in for S and B. Now I have my inequality that I can use for the situation. So the second part to this is, what does the graph look like? The graph is our solution set. So if I go in and graph this, I would get a line that looks something like this. I chose to cut off the line at the axis because it doesn't make sense to have negative pounds of blueberries or negative pounds of strawberries. We can see from this inequality it's a solid line because of the symbol. That greater than or equal to sign makes it a solid line. Now, the second part for inequalities is our shading. In this situation, we want our items to be less. So we would need to shade below the line. This shows that anything in the shading could be a solution. So for example, if we bought 2 pounds of blueberries and 2 pounds of strawberries, we would end up with a total of $11. I plugged in 2 for X and 2 for Y. 11 is less than 15, so we didn't spend all the money. We're fine. Anything that's in this shaded area works. And because it's a solid line, anything that's on the line also works. The line would just be those totals where you spend exactly $15. Now it's your turn. Pause the video, read through the situation, try to graph it, and shade to show the solution for the inequality. Use Desmos for help if you need to, but don't forget, you can only use X and Y. Let's check. Your inequality should have been 1.50x plus 0.75y is less than or equal to 10. It tells us that lentils are X, and lentils cost $1.50. Garbanzos are Y, and Y costs 75 cents. Again, they're spending money. They only have $10. They can spend all of it or less. Your graph, the line would have looked like this. It is a solid line and shaded below. And again, anything in the shaded area or on the solid line works as a solution or a possible combination for lentils and garbanzos here that could work for this situation. Let's look at another example. A school wants to raise more than $500 from the school carnival by selling student tickets for $2 and parent tickets for $5. What inequality represents the possible combinations of attendees to meet their goal? First, let's write our inequality. Here it says we want to raise more than 500. So it would be greater than 500. If you're not sure if it's greater than or equal to, think about if it could be that number. Is 500 more than 500? No, it's equal to, but it says more. So it can't be equal. So more than 500, how are we going to get that? We're going to get that by selling student tickets X for $2 and parent tickets Y for $5. So based on that and the symbol, the line would be dashed, and more is above, so I would shade above. Anything in the shaded region here would work to raise more than $500. For example, if we sold 300 student tickets, no matter how many parent tickets we sold, we're always going to be in the red. Or if we sold 200 parent tickets, no matter how many student tickets we sold, we're always in the red, which means those things work. Okay, this is our shaded area. If you're given a situation, so say 100 students and 100 parents attended, did they make enough money? You would look, 100 students, 100 parents, it's in the shaded region. Yes, they made enough money. What if only 50 parents and 50 students attended? Well, 50 parents, 50 students would be about here. That's not in the shaded area. They didn't make enough money. So again, in the shaded are all the possible combinations that work. Pause the video and try yours out. Again, using Desmos if you need it. For extra practice, When you're done graphing it, see if you can figure out if 300 students and 200 parents showed up, did they meet their goal? Check your answer. First, your inequality, 5x plus 8y is greater than 3,500. If you put 8 with x and 5 with y, it's not a big deal because it doesn't tell you which is which here. Your graph will just look slightly different, but your combinations will still be the same. Your graph would look something like this. Again, it's a dashed line as our boundary and shaded anything above. If your graph doesn't look exactly like mine, notice the scaling on mine. I'm counting up by quite a bit each time. If 300 students and 200 parents showed up, did they meet their goal? If we check 300 and 200, so 300, 200, that point would not be in the shaded area, so it would not have worked. Not enough people attended to make their goal. Again, it would have had to have been in the shaded area for the inequality to be true. In this lesson, we learned about graphing in context. So in context, graphing a linear inequality shows all the possible combinations that work for the situation. Any coordinate, so the combination of the two items or the two sets of people, any of them that fall in the shaded region or on a solid line works for that situation. So for example, if you went to the fair and found you could buy food tickets for $2 or ride tickets for $3, but you only brought $30 with you, you wanted to figure out how many rides you could go on, how much food you could buy. There are different combinations for each. If you wrote that inequality, such as 2x plus 3y is less than or equal to 30, the shaded region would tell you all your possible combinations. So the coordinate 2, 5, meaning 2 food tickets and 5 ride tickets, is in that shaded region. So if you bought that combination, you would spend less than $30. In fact, you'd only spend $19, which is definitely true that it's less than $30. One caution though, and I did sort of mention this earlier, when you graph, especially using Desmos, it's going to shade all values that work, including your negatives. But in context, a lot of times it's impossible to have negative values. So just be cautious and use common sense about choosing which values actually work. After this lesson, do you know how to write an inequality from context? And can you graph the solution set and explain what it represents? If you're not sure about those things, go back and look at a couple of the examples to help further your understanding of this concept. And that's the end of lesson 5 of solutions of two-variable inequality from context.